Hello everyone. In this lecture we are going to see one topic that is called phase time diagram. Okay. So previously we had seen that if instruction I1 has to be executed, it has to go through all these phases, right, one by one, and when it come out from last phase we can say that it is executed or it's processed, right? So in this lecture what we are going to see is that how this phase time diagram works, okay, using these particular phases. Now you might be observed that these particular phases, okay, they are working whenever any instruction passes through it, there would be some operation will be done, right, inside this particular phases, right? Now how it is done? It is because there is some combination circuit inside this particular phases. Combination circuit is assigned to this particular phases. See, combination circuit, I think we already knew in digital logic, we had learned it, right? So those circuit will be assigned here. Fine. So that is how this particular phase will work. Okay, they can take care of each other. That combination circuit will take care of that particular phase. Fine. So in order to do this, in order to do this phase time diagram, we are going to split up the hardware in the CPU into various functional unit. We have already seen the functional unit, right? And we dedicate each unit for each phases. That is what we have done by assigning the combination circuit, right? And by doing this, we can ensure parallelism. Okay, this is how we get the parallelism, right? So here we will see about the phase time diagram. Okay, so we will see without pipelining also. So how this phase time diagram will look like and all those things we will going to see. So first we will see without pipelining. Okay, so what we are going to do is, suppose we are going to execute two instructions. Okay, and then how many clock cycles will be required to execute that two instructions? That is what we are going to see. Okay, so how many time will be taken so that it will complete its two instruction will be completed. And we already knew one thing, that each instruction requires 4 stages or phases, right, to complete its execution, right? So keeping all this in mind, let's draw one phase time diagram. With this we will understand that how it will work. And this phase time diagram I am going to draw according to that. I am considering that it is without pipelining. Okay, I am not using the technique, pipelining technique. Now I am designing it. What happens if it is without pipelining? Okay, so let's see how many clock cycle it will take without pipelining. So we already knew that each instruction will take 4 phases. That is, first is instruction fetch, then instruction decode, like this. So it will take these 4 phases, right, each instruction. So I will draw like this. Then what I will do is I will keep it in a vertical way. Then okay, so at the dimension, at the attributes, I will put clocks. Okay, how many number of clocks is going to take. So this is just to make it simple. Okay, so with this you can understand how many clocks you are going to take when you execute one particular or two particular instructions, right? Now in the column we are going to add clock cycles like 1, 2, 3, like 4th clock cycle, 5th clock cycle, 6th clock cycle, 7th, like so on. You have to keep on adding it, right? So I am going to add till 12 clock cycle. So how I know that I have to add 12 clock cycle? This is because I already solved this question. Okay, that's why I know that there would be a 12 clock cycle. So when you are solving it, you have to keep on adding these clock cycles. Okay, so unless and until you will complete the 2 instruction. Okay, so you keep on doing it, you will get it. Okay, so you will understand when I solve the problem, don't worry. Okay, so here there is a clock cycles, right, and this is for phases or stages. This row is dedicated for phases, or you can call it stages, right? Now let's see how many clock cycle will be taken for 2 instruction to complete its execution. okay, without pipelining. So if I write, for example, I1 here, what does it mean? It at first clock cycle, and at first clock cycle I1 is at phase, instruction fetch phase, okay, that is the meaning of it. And then after that I1 will move to, at second clock cycle I1 will move to decode phase, okay, that is the meaning of it. So when I write I2 here, that means at second clock cycle sorry, it's not I2, it's I1, okay, I1, okay. So what does it mean is, at first clock cycle I1 will move to instruction fetch, and after that at second clock cycle I1 will move to instruction decode phase. Then I1 will move to execution phase at third clock cycle, and at fourth clock cycle I1 will move to this write back phase, right? So after this write back phase, I1 will complete its execution, okay, it will complete its execution. So how many clock cycle it had taken? It had taken 4 clock cycles, right, to complete its execution. Now after that, what will happen? I2 will start its execution, okay. So at fifth clock cycle I2 will start its execution, and at fifth clock cycle I2 is at fetch phase cycle, right, at fetch phase. Now at sixth clock cycle I2 will move to decode phase, okay, and at seventh clock cycle I2 will move to execution phase, and at eighth clock cycle I2 will move to what? Write back phase, and after that I2 will complete its execution, right? So how many at how many clock cycle? It had taken 8 clock cycle to complete its execution, okay. So we can clearly see that to complete 2 instruction it had taken 8 clock cycle. See, this is without pipelining I am talking about, okay. So you can clearly see one form, you can derive it without formula also. See, for one instruction it is taking 4 stages, and for each stage is 1 clock cycle, right? So 4 clock cycles. So for one instruction it is taking 4 clock cycles. So for 2 instruction it will be 2 into 4, 8 clock cycles. That is what we are derived here using a phase time, right? Now we will see one thing, that with pipelining how we can improve this clock cycles, okay, how we can improve this performance, okay, fine. So we will see that part. Now let's say at first clock instruction 1 is at fetch phase, but it is fetching an instruction, okay, and second, now at second phase at clock 2 instruction 1 will be at decode phase, right? At clock 2 instruction 1 will be at decode phase. Now you can clearly observe one thing, that this particular phase, that is instruction fetch at clock 2, is idle, okay. So back then, now we are using pipelining technique. So what pipelining technique says, that why you have to keep this particular phase idle, you can utilize it, right? So what I am going to do is that in this phase only I will keep fetching I2, right? So at clock 2 now I2 is at fetching phase and I1 is at decoding phase, right? Now at clock 3 what will happen? I1 will move to execution phase, right, and I2 will move to decoding phase, and you can clearly see that this particular fetch cycle at clocks at third clock is idle, okay? At clock 3 it is idle, right? So why to waste that time, right? So you utilize it. So how can you utilize it? You fetch one more instruction. So I am going to fetch I3 now. Getting it? Right. Now at fourth clock what will happen is I1 is at write back phase, and our I2 will move to execution phase, right, and I3 will move to decode phase, right? And you can clearly see that fetch cycle, this fetch phase is empty. So why to make it empty? You start utilizing it. I will start fetching I4, means instruction 4. See, this is where the parallelism came into picture. Back then what was happening is, without pipelining, this particular phase, you can clearly see this particular phase. Say for example here in third clock, when I1 was in execution phase, decode phase and fetch phase was empty, means it was idle, right? We are not utilizing that particular timing. So here in pipelining, we are fetching multiple instruction at that particular clock cycle. That is where the parallelism came into picture. Okay, so this is how it is simulating the parallelism, right? Now you can see at fourth clock cycle, I1 will come out, right? So it had taken 4 clock cycle for I1 to complete its execution. Fine. Now I2 will, at 5th clock cycle, I2 will move to write back state, right? And I3 will move to execution phase, and I4 will move to decode phase, and still it is some fetch phase is still empty. So you can utilize some other, you can use something like I5, right? So you can clearly see that at 5th clock cycle, I2 has already completed its execution, right? So to complete, for I2 to complete its execution, it has already taken 5 clock cycle. It has only taken 5 clock cycles. So back then, it is with pipelining, and back then we can see to complete 2 instruction, it was taking 8 clock cycles. See, I2 was taking 8 clock cycle, and here in pipelining you can clearly see it is taking only 5 clock cycle. So it is, you can see the improvement, right? So using pipelining, you had improved the efficiency, everything was improved, right? So this is how we improve the performance, right? So this is what I want to show you, that how pipelining will improve the performance and everything. You can continue this, okay? See, you can see at every, after 4 clock cycle, at every clock cycle 1111 instruction will come out. Okay, if you want to see, I will complete this particular thing so that you can understand the next part. Okay, fine, I will complete this. Now you can clearly see that at 6th clock cycle, I3 will come to write back phase, I4 will come to execution phase, and still decode, and at decode phase I5 will come, right? And you can still start your execution, right? You can use this, utilize this fetch phase. That's it, right? So you take I5, right? So you start executing I6, means start fetching I6 at 6th clock cycle. So you can clearly see at 6th clock cycle also, I3 came out at 6th clock cycle. So to come out, for I3 to complete its execution, it had taken only clock cycle, or 6 clock cycle, right? I will do one more thing, you will understand, okay? Now you can see at 7th clock cycle, I4 will move to write back phase, and I5 will move to execution phase, and I6 will move to decode phase. And here itself you can fetch one more cycle, that is one more instruction, I mean, that is I3. Now you can see that at 7 clock cycle, after 7 clock cycle, I4 will complete its execution. Can you see that? So what you observe is, so you can clearly see that after 4 clock cycle, I1 will come out. After 5 clock cycle, means at 5th clock cycle, I2 will come out. At 6th clock cycle, I3 will come out. At 7th clock cycle, I4 will come out, so on, right? So for I1 to come out, it has taken 4 clock cycle. After that, I2 I3, I4 within one clock cycle they are coming out, right? Within one clock cycle. So the first instruction had taken 4 clock cycles. So how can I derive is like first instruction, that is I1 has taken 4 clock cycle, right? That means first instruction. And after that remaining instructions, okay, will take only 1 clock cycle to come out. Okay, so this is something you can derive, you can observe from it, from this particular phase time diagram, right? So first instruction has taken 4 clock cycle. So first instruction has taken 4 clock cycle, and after that remaining instruction is taking only one clock cycle. Okay, so this is how pipelining will work. So this is something I observe it. So you can formulate one formula with this, right? So how can you calculate? So let's see this this example. Let's see this exercise. Suppose there are 4 instructions, okay, to execute. Then tell me how many number of clock cycle will be required. Okay, so how can you calculate? So let's calculate using a formula itself, right? So we know that first instruction to come out, okay, one instruction to come out, it will take 4 clock cycles, right? And the remaining, what is remaining? Remaining, that means 4 minus 1. For remaining instruction, it will take only 1 clock cycle, right? So if you calculate this, it is 4 clock cycle plus remaining is 3 into 1 clock cycle, right? So that is 4 plus 3 is, sorry, 4 plus 3, right? 4 plus 3 is 7 clock cycle, right? So is it right or wrong? 7 clock cycles. So you can clearly see, let's see, for 4 instruction, if you take 4 instruction, then it will take 4 clock cycle to complete its execution, right? Yeah, fine. So this formula is on the basis of pipelining. If you are considering pipelining, okay, then this is the formula which is valid. Okay, so I hope you understood how to calculate all those things. We will try to generalize this formula. Okay, this is not a generic formula. So consider there are n instruction. Okay, so I will try to generalize this formula so that it will be very easy for you to solve in exam also. So suppose there are n instruction, okay, in the pipeline, and total you have to calculate total number of clock taken or time taken, okay, if there are n instruction in a pipeline manner. Okay, now suppose the total number of clocks taken is TP. Okay, I am just denoting it with something called TP, and the number of phases is M. Okay, total number of phases, and the number of instruction is N. Okay, so these are the notation I am using. Okay, you might be thinking, what is this number of phases, right? Okay, this. Okay, now you might be wondering, what is this M, number of phases? Okay, so what is this number of phases? What do you mean by this M, right? See, you have to understand one thing. We are already seeing that one instruction takes 4 stages, right? And each stages takes 1 clock cycle. 4 stages means instruction fetch, decode, execution, write back. That is what I am talking about, right? So each stage take 1 clock cycle. So total 4 clock cycle in our pipeline. So if there are 4 stages, then we have 4 clock cycle. Like this, if there are 5 stages in our pipelining, then it will take 5 clock cycles, right? One instruction has to go through 5 stages at the beginning, if there are 5 stages. Then if there are 6 stages in our clock cycle, then first instruction has to go through 6 clock cycles. Then there will be 6 clock cycles. Like this, if there are m stages, right, then it will take m clock cycles. The first instruction has to go through all the m stages, that is m clock, then it will take m clock cycle. That is the meaning of it. So with this we can derive one thing, that number of clock cycle is equivalent to number of phases here. Can you see? Number of clock cycle is equivalent to number of phases here, right? So this is what you have to keep in mind, right, solving the problem. So we will see now. So now if I want to come up with some formula, then For example, what is the total number of clocks taken or total number of time taken, that is TP. Then for first instruction, one instruction has to go through m phases. That means it will take m clock cycle, right? Then after that, remaining instruction will come out within one clock cycle. So remaining instruction means n minus 1, that is remaining instruction. So remaining instruction will take only one clock cycle. So at the beginning, first instruction will take m clock cycle. After that, remaining n minus 1 instruction will take one clock cycle. So this is the formula you can come up with. Are you getting it? So whenever I am talking about pipelining, you can directly put this formula and calculate the number of clock cycles. Okay. Now this is the generalized one. I written it in a generic way. So TP means total number of clock cycle clock taken, and for this part, for the first instruction it takes m clock cycle, that is what I had written, and for the remaining n minus instruction it will take only one clock cycle. That is what this part means, right? So this is all about pipelining. So this is the formula for pipelining when you are using a pipeline. So let's see for without pipelining also how many time taken. So we just try to generalize the formula for without pipelining also. So without pipelining, you can say, if I am asking the time taken, so I am denoting time taken without pipelining, that is TWP. That is the this is a notation I am giving. Okay. So if there are n instruction, then each instruction will take m phases, right? Each instruction will take m clock cycles, right? So that is what I am taking. This will give you a formula. So for executing an instruction, every instruction is going to take m phases. That's why n into m. Okay, let's take one example. You will understand better. So for 5 instruction, let's take for 5 instruction how many clock cycle is going to take. Okay, so for without pipelining, 5 into 4, that is 5 instruction is there. Each instruction will take 4 clock cycle, then 20 clock cycles, right? But with pipelining, can you improve it? So let's see. First instruction will take 4 clock cycle, right? After that, remaining, that is remaining instruction is 5 minus 1, that is 4, will take only 1 clock cycles, right? That is what I written, 4 in 4 and here 4. So 4 plus 4 is 8 clock cycles. You can clearly see the improvement. Okay, without pipelining it is taking 20 clock cycles, and with pipelining it is taking 8 clock cycles. Okay, so that is how the pipelining will improve the performance. Fine.